Hey, good afternoon, everyone. Happy Halloween. Hope you have, had a chance to relax just a little bit and hopefully get some candy or something from somewhere. There's always events going on around campus. All right, let's get to our discussion. So I believe we had stopped here. We were discussing and talking about voltage dependent sources. And we had seen that there are four kinds of dependent sources. We can use these as models um, models for different semiconductor devices in many of our circuits. All right, does anyone have any questions before I proceed? Okay. All right, so continuing with the theme of elementary parametric circuits, let's just talk about the concept of a switch. A switch is a binary device. It only has two states. It's either on or it's off. In terms of resistance, we can specify a switch as having two separate values. If the switch is on, meaning it's allowing current to pass through, we can say resistor R is small. For an ideal switch, if it's on, then R would be equal to 0 or 0 ohms, 0 ohm resistance. And if it's off, then we can state that the switch has infinite resistance. Okay, so it's a binary device, either on or off. And you have a mechanical switch or a digital switch, it's either allowing current to pass through or it does not provide any pathway for current to flow through. Okay, so real life switches, resistance R would be small, and when it's open, infinitely large. Okay, now switches can come in a variety of physical shapes, sizes, but we can also implement switches using semiconductor devices. Okay, there are special purpose transistors that we can use as a switch. These form the primary backbone of digital logic circuits, right? All digital logic circuits, that we use nowadays, they're based on either the switch or the device being on or off. Okay, so you all have taken 133, CP 133. You've done a little bit of digital design, right? You've learned about the binary number system in there and what it represents. Now that's the design part of it. That's the binary math part of it. When it comes to circuits part of it, it still is voltage and current. Okay. So typical digital system, let's say it goes from 0 to 5 volts. Then if it's 0, or we say it's logic 0, meaning it's 0 volts and 0 current, ideally. And when it's logic high, we use binary number 1 to represent logic high. But in terms of circuit voltages, it would be plus 5 volts. So you have digital circuits between 0 and 5 volts. Modern circuits are between 0 and 3.3 volts. So logic 0 or 0 would be 0, and logic high 1 would be 5 volts or 3.3 volts. So there are many semiconductor switches that you can create and use voltage or applied voltage as a controlling mechanism. Meaning we apply a certain input voltage in the switch, and the device behaves as a switch. Depending on the design of the system, depending on the applied voltage, the switch can be either on or off. Okay, and that's something you probably studied in 133. You can buy these off the shelf. These microchips don't cost a lot. Here is an example. Chip number is 4066, labeled here, 4066. It's a quad bilateral switch, meaning there are 4 switches on this chip. 14-pin chip. There's 1, there's 2, there's 3, and there's 4. 3 pins for each, 12 pins, and then you have 1 pin for the plus 5 volt supply and the other one for ground. Okay. Typically in logic ICs, pin number 7 or pin number 8 is typically ground, and pin number 14 or pin number 16 is plus VCC. So as I was saying, we can buy these microchips off the shelf. They are voltage control switches. So based on the voltage that we apply, the switch can be controlled on or off. Okay. And bilateral simply means it can go in both directions. Okay. So let's take the example of the first switch. So between pins 1 and 2, you have this device. And based on the voltage applied to pin number 13, that voltage will be the controlling voltage where it decides whether the switch will be on or off. Okay. So the voltage that's applied to pin number 13 must be between 0 and VDD. VDD, here it lists 3 volts to 18 volts. Typically, I would say if it's digital, then we'd stay between 0 and 5 volts. But the chip is designed to accept all the way up to 18 volts. Okay. So that's a voltage control switch. What you're going to look at next is a VRD circuit. VRD stands for voltage, resistance, and diode. Essentially, it's the simplest form of a diode biasing circuit. You have a single diode, and you're applying voltage to it. Okay, and the resistor is used to limit the current. Hence VRD. Okay, VRD. This forms a series circuit. And so the current that flows through the circuit is the same for all. We can call it IR or ID. It does not really matter. Okay, the resistor current is the same as the diode current. So IR and ID are the same. Now, a real life example would be applying a voltage to a LED. LED is a diode, and our voltage source could be like a benchtop supply, could be a battery, 3 volt battery or a 9 volt battery perhaps. And then we'd want to insert a resistor in the middle to limit the current that is flowing through that circuit. Remember the previous example where we were trying to apply a voltage to a LED to turn it on, but we didn't want to burn out our LED, meaning our goal was to have a specific voltage across the diode, across that LED, and a specific current flowing through that LED. And so it's a similar example. What do we do if we want to have a specific current or specific voltage going for a diode? Okay. Now, at this point, let me introduce what is known as the diode equation. We talk a little bit about that. So the first semiconductor device that was created and presented was the solid state transistor. So it was a germanium transistor. And this was a result of an effort that took place in the 1940s and the 1950s at Bell Labs. 3 people, William Shockley, John Bardeen, and Walter Brattain. They ended up winning the Nobel Prize just a few years later for their invention. Okay, and William Shockley was one of those 3. He was right here in California. And he came up with this equation to describe the flow of current in a semiconductor device. Okay, it's a semiconductor device, just P and N type material. So PN junction diode, and literally provides the relationship between diode current and diode voltage. Remember, the diode is a non-linear device, right? For a resistor, we have V equals IR, Ohm's law. For a diode, it's far more complex device, okay? Even though it is considered to be the simplest of all semiconductor devices, but it's a very complex device, non-linear, and we use different models to explain the analysis of diode circuits. But this equation is fundamental to all semiconductor devices. Okay, so if you have a simple semiconductor device, this equation is used to describe the flow of current and the voltage that appears in that device. Okay, so there are three components in here. There is IS, there is N, and there is VT. Okay, IS stands for saturation current. Saturation current. And again, this is something you will study in EE 315. Saturation current, the only thing you need to understand for now is that it's fundamentally present in all semiconductor devices, and it is very, 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 very small. Okay? Typically, when we measure the saturation current in the lab, it's nanoamps or less. So sometimes you need specialized equipment to even measure this accurately. So it's very, very small. Okay. If you run a simulation, saturation current is usually 10 raised to minus 12, 10 raised to minus 13, 10 raised to minus 14. Almost close to like femtoamps. Okay. So the last lab that I did in one of my other classes, I think diode saturation current was 10 raised to minus 10. So less than a nanoamp. But it is a fundamental quantity in a semiconductor device. Sorry. Saturation current. Without going into a lot of discussion, it requires a lot of explanation. I'm trying to find the best way to summarize what a saturation current is. All right, a semiconductor devices are made up from two different kinds of semiconductors. There is a P-type material, there's an N-type material. When you bring a P and N-type material together, we get what is known as a PN junction. A PN junction, so P-type material has an excess of holes as semiconductor carriers, and N-type material has an excess of electrons as semiconductor carriers. When electrons flow, they're carrying the charge with them. Holes are the exact opposite of electrons. It's the absence of an electron that creates an empty spot inside a semiconductor material. So it's a hole. So it's positively charged. Electrons move one way, holes move the other way. And so in an N-type material, there is an excess of electrons. They are known as the majority charge carriers, and a very few number of holes. So those are known as minority charge carriers. In a P-type material, you have an excess of holes, meaning more positive charges and fewer electrons, so less negative charges. So they are minority carriers. So when we bring P and N-type materials together, there's a junction interface. It gets depleted of all charges. There are only minority carriers present on both sides. So when we apply a voltage on opposite sides of the PN junction, there is a small current that results because of the flow of minority charge carriers. That is known as the saturation current. The reason it's so small is because the amount of these charge carriers, the number of electrons and the number of holes is very, very small compared to the other majority charge carriers. But again, that's about as brief as I can get with describing that. Again, that is a topic for spring when you will take 315. Okay. N is the non-ideality factor. It basically just describes the non-ideality performance of the diode. Is a manufacturer's spec. Typically, it's between 1 and 2. So the manufacturer's data sheet will list what that factor is. If it's not given, we typically assume just 1. So it's between 1 and 2. And the data sheet usually lists this number. But for most applications, we simply assume 1. A VT is the thermal voltage. Thermal voltage is the voltage that results due to the differing motion of the holes and electrons, and due to varying temperature. Okay. So VT is given by KT over Q, where K is the Boltzmann's constant. T is the temperature in Kelvin in K, and Q is 1 unit charge. So everything is a constant except for the temperature. By the way, has your department told you about your flowcharts? The courses that you need to take? Yeah. So the E series 115, 215, and 315, 115 is being offered now. Is being offered, one section offered next quarter. 215 is offered in winter, which I'm assuming you all will take. And then 315 is in spring. That ends your sequence. And then for those of you who come after you, 115 is offered in winter and 215 is offered in spring, but there will not be 315 offered after that. So 315 will be offered for the final time only in spring. So if a student doesn't make it through the sequence, as you know, there'll be a lot of students who are coming after you. They'll be taking 115 and 215 in fall, in winter and spring. Then they will be taking 3306 in the semester version. So you'll be taking it along with the E students. Okay, so just letting you all know. 315 will be offered for the final time only in spring. All right, so that is the diode equation. For most applications, we can reduce the equation by approximating it as IS times EXP, E raised to ED over VT. Okay, we ignore the 1 and we ignore the N. And so it simply becomes saturation current times E to the power of VD over VT. So ID and VD have a exponential relationship. Okay. So question is, if you are given the voltage value and the resistance and the diode characteristic, calculate and determine ID. Okay. Determine ID. So let's just do that. Okay, here is a LT-SPICE simulation and a calculation. So we'll do it manually, and we'll also do a computer simulation. Okay. So supply voltage is 10 volts. Model of the diode is given. When we open up the model of a diode inside the SPICE simulation software, there are different parameters that we can substitute. This specific model has a saturation current of 1 into e raised to minus 22. Okay, e raised to minus 22. Very, very small saturation current. RS is a series resistance. This is typically very small. And for the most part, we ignore it or we take it only as 1 or 2 ohms. Okay. So typically we just ignore it or we take it as 1 or 2 ohms. All right. And N is given as 1.5. There are a few other things in there that you won't worry about. Again, that's for E315. Right now, again, you're not studying the diode as a device. You're simply using the diode as an off-the-shelf component to apply to different applications. Okay. All right. So what is desired is that we want to keep the diode current to approximately 50 milliamps. Assume that the room temperature gives us a thermal voltage of 26 millivolts. Typically is about 25.8 millivolts at 27 degrees C. Room temperature means different numbers at different places, right? Here in this room, if I was to take the room temperature, it'd be about 70 to 75 degrees Fahrenheit, which translates to about 20 degrees C. Elsewhere, room temperature might be 27 degrees C, which is 54. It's about 86 degrees Fahrenheit. So room temperature is generally between 70 and 80 Fahrenheit. Okay, so we take all our values that are given to us, plug it into the equation, and we obtain, what do we obtain for VD? VD, we come up with as 1.86 volts. Okay. So ID gives us the diode equation. We rearrange the terms and we can write an expression for VD. Okay. We are given the saturation current. We are given the diode current, which is 50 milliamps. And we have N, we have thermal voltage VT. At that point, it's simple plug and solve. Okay. Now, all of these examples, they've already been solved. So the answer is already in front of you. But I would strongly recommend students, whether in class or outside of class, when you're reviewing these lectures, you should do these by yourselves to ensure that you are able to solve these two. The advantage in this is that this has already been solved. The procedure is laid out and the calculations are also, and the final answers are also available to you. Okay. But for your review and for your learning, you should definitely go through these on your own. Yes. Absolutely. Yep. So a question being asked was, should we do these as preparation for quizzes? And the answer is yes, absolutely. Okay. So now the next part of our next part of the design is that we want to calculate the resistor value. Okay. Since we found the diode voltage is 1.86, the diode is dropping 1.86 volts. That means the resistor must drop 8.14. Okay. If you are limiting the resistor current to 50 milliamps and the diode voltage to 1.86, then the resistor voltage is 8.14. Apply Ohm's law, and we obtain the value as 163 ohms. 163. In real life, you will not be able to find 163 ohms because resistors are manufactured with certain values. Okay, there's a series of values that are used to manufacture resistors. So 163 ohms is not available off the shelf. If we wanted to, we could combine multiple resistors in series or parallel to create an REQ of 163. But the closest single resistor value would be 160 ohms. Okay, so if you're really designing a circuit and we wish to use it, then we would use an off-the-shelf component 160 ohms. Okay. Right now, we are ignoring the series resistor. Yes. 8.14 volts is 10 minus 8.6. So we applied KVL around the loop. And V is, again, as 10 volts. VD, we determined to be 1.86. And so then VR, the resistor voltage, was 8.14. Question? All right, let's take a pause. Let me know if you have other questions. The voltage across the diode is the same as the voltage across the resistor. The voltage is not the same. Diode voltage is 1.86 volts. Resistor voltage is 8.14. Diode voltage is here. And then this is resistor voltage. The current is the same. Current is the same because it's the series circuit. So current for the voltage source is the same as the current for the resistor, is the same as the current for the diode. So current is the same for all because it's a series circuit, but the voltage is not the same. Other questions? Okay. All right. So in this simulation, as it states right there, we are ignoring RS for now because RS is small compared to the resistor voltage. I mean, the resistor value. All right. Here is the LT-SPICE simulation. When we simulate this in SPICE, we obtain a diode current of 49.1058 milliamps. 49.1 milliamps. Okay. And look at that voltage, 2.14. Okay. Why? Because we ignored the 6 ohms in our manual analysis or manual calculations. If you had included the 6, we would have taken 160, or we would have added it on, and we would have been able to obtain the voltage drop inside the diode. Okay. So that would have been added on to the diode voltage. So it would be 1.86 plus 0.3. In a SPICE simulation, the RS was entered as 6 ohms. In a manual calculation, we did not use the 6 ohms, right? If we did enter the 6 ohms, it would have turned out like this. This would be the R, and this would be RS for the diode. And then we'd use diode voltage separately. But because we ignored the RS, our value for the resistor or the voltage across it is slightly smaller. So diode voltage along with the series resistance voltage will have a slightly higher voltage drop. The difference is about 0.3 volts, which kind of makes sense because our current or our circuit is designed for 0.05 amps. 0.05 times 6 gives us 0.3. Do you have a question? Yes, that is correct. RS is the internal resistance of the diode. It is part of the diode, so physically we cannot separate it out. But electrically speaking, we can draw it out as a resistor in series with an ideal diode. Yeah. Okay. All real life devices have this quantity. All right, let's take a pause. Let me know if you have any other questions. Any questions? Okay, so at the bottom you have, yes. Question being asked is, does the SPICE simulation ignore the RS or does it take it into account? It takes it into account. We ignored it in our manual calculation. The SPICE simulation takes it into account. So RS is set in there. So LT SPICE is really good when we want to create a graphical, like a graphical circuit, graphical interface. So it's really good and powerful for that. But it has a limitation where it will only allow us to use the models that are available in its library. So we can't really modify any of those models. We'd have to do a SPICE directive. So if you wanted to, like, let's say, use any kind of random diode with no RS, then we'd have to type everything up. We can't use a diode model like this because it just wouldn't allow us to modify any of its parameters. So yeah, answer to your question is that SPICE does not exclude those quantities. It always includes it. So you can simulate this using 3 such diodes in series and to limit it to 50 milliamps using the same 10-volt source. And see if you can come up with an answer. All right. Okay, further analysis. How can we use the equation to solve it directly? So we have this model, everything is given to us. We are asked to find ID. Okay, asked to find ID. We're only told VD is greater than 0. Voltage source is given as 10 volts. Resistance is given as 270 ohms. Right? 270 ohms. So if we apply KVL around the loop, what do we get? If you apply KVL around the loop, we get the source voltage Vs. Let's write down Vs R, and then this would be Vd. So Vs would be dropped across the resistor. So Vr across the diode Vd. Vr can be expressed using Ohm's law. So I can write 10 is equal to IR. I is ID times 270 ohms. And then Vd I can write from the diode equation. So NVT times the log of ID over IS. Okay. 10 is equal to ID times 270 plus NVT log of ID over IS. Now, These kind of equations are known as transcendental equations because they involve log, exponents, those kind of functions. One downside of these kind of equations is that there is no closed form solution. We cannot simply plug in the values and expect a single value answer. It's just not possible. Okay. So the way to solve these is by a process known as iterative analysis. We do multiple iterations. So we first pick a value, solve the equation, then we match the answer to our chosen value. If it matches, then our chosen value or assumption is correct. If it doesn't, then we go back to the top, we change our assumption at the top, and we reiterate and redo the calculation. At the end, again, we check and verify whether our answer matches our assumption, and we keep repeating the iterations until our answers match up with our assumptions. Okay. So here we have that equation, right? It's the same equation. We take that equation, we choose an initial value for VD. Okay. Choose an initial value for VD and we calculate ID. Okay. So if we do that, the most basic place to start is that it's an ideal diode. There's no voltage drop across the diode. We start with 0, just to show you like the lowest possible starting point, right? Lowest possible starting point is diode voltage as 0. So we do that and we obtain 37 milliamps. Okay. Now, once we have 37 milliamps, we plug that back into the equation. Everybody with me so far? We chose a starting point. We chose VD as 0, calculated ID. We obtain ID as 37. I'm going to plug that into the equation. Once we plug it into the equation, then we calculate VD. So when we plug 37 into the equation right here, we obtain a VD of 1.847. Before you note it down, just follow this with me, okay? Then once we obtain 1.847, we plug it back into this equation and calculate ID. So we plugged in 1.847 here, calculated ID here, 30.2. So a second iteration, our current has dropped from 37 to 30. Are you all with me so far? And when we plug 30 milliamps back into the equation, which is here, we obtain a diode voltage VD of 1.839. Very, very close to the previous step. 1.84 and 1.839. Not exactly the same, but for the first decimal point, 1.8, 1.8. Within 2 steps, within 2 iterations, right? First, we started with 0, obtained 37, plugged in 37, obtained diode voltage. So what we are doing here is we picked a starting point. Our starting point was diode voltage. So let me just draw kind of like a flow chart here so it makes sense. Why is it doing the arrow? So we chose VD as equal to 0 volts, calculated ID. So I'm going to say from this, calculated ID. Then from calculated ID, we calculated VD. From VD, we again calculated ID. And that's what we did. Actually, we did this. So from 0, we got 37. From 37, we got 1.84. From 1.4, we got 32. Sorry, we got 30. From 30, we again obtained VD, and then finally we obtain ID. So 1, 2, 3 iterations, if you will. Okay, 3 iterations. So let's take a pause while you absorb all of this and let me know if you have any questions. I'm going to wipe all of this out so it's clean for you to make notes. Have you all seen this iterative process before? Okay. So good question. Question being asked is, would we always do 3 iterations? The answer is no. The correct answer for this would be, it depends on our application and how many decimal places we want in our final value. So let's say I was working for a group, and then my boss says, it's a hypothetical scenario, if I'm working in a company, our boss or team leader says, no, we need it to match at least to 4 decimal places, right? And then this would not be sufficient enough because ID in this case, well, first of all, my voltage does not match beyond the first decimal place. 1.8, 1.8, yes, but it's 1.847 and it's 1.839. So if our team lead says, no, we need to go up to 4 decimal places where it matches down to the millivolt, right? It must match down to the millivolt range. Then we need to make sure everything matches up. So then we keep iterating the process until we obtain those values. Even in the current, right now it's 30.20 and it's 30.22. So it's only matching up to the first decimal place. And we need to take more significant digits. So it just depends on our application. That would be the answer. Yes. Sure. Oh, wait. Okay, no, so sorry. Go ahead. Finish your question. Can we use that value for? Yes. So here, let's draw some more arrows. From here, we calculated this. From here, we calculated this. From here, we calculated this. From here, we calculated this, and we finally got this. That's how it went. Yes, that is correct. Okay. Yes, clarification. Yes, that's a good observation. It's just easier. It's just easier. So the observation being made here is that we are not actually calculating the diode current from the diode equation. We are calculating it by applying Ohm's law to the resistor itself because it's just easier. We can do so by applying the diode equation again, and we can certainly obtain values for that. We just did a similar, I'll wait here for a few more seconds and then. Does that make sense to everyone? Right? So I'll show you this example, which I'm doing for my 300 level semiconductors class. And let's see. E306 and chapter 3. There we go. So this is the semiconductors class, which CP students will take when they get to semesters. Okay. Here we are trying to determine the Q point for the diode, and all we were working with was the diode equation. Okay, again, transcendental equation, so we can't solve them by regular means. So we obtain the expression first from applying KVL to the circuit, and this is the equation we obtained. So now we have VD on both sides of the equation. It's a transcendental equation, has log, natural log inside it. So I created, and this is the simplest possible way to do it. But we can do it in MATLAB, which, by the way, if you've not yet started learning MATLAB, you should start learning MATLAB. It's a good skill to have. The software licensing is available for free to all students. So you can program this equation in MATLAB and run the iterative analysis that way. This was simply done in a spreadsheet in Microsoft Excel. You can do it in Google Sheets also. So I had this equation. I programmed it right here at the top, right? And I started with an initial assumption of 0. I started with an initial assumption of 0 for the diode voltage, and I obtained the answer for the diode voltage is 0.594. So my goal here in this example was to obtain the diode voltage, but the equation that I had for the diode voltage did not allow me to have a direct solution. So what I was doing here was, excuse me, that I have this equation for diode voltage, and I choose the diode voltage initial starting point. I choose it as 0 volts. So I plug in VD as 0, and then I solve the equation. Okay. This is the equation that I have. VD is equal to VTln 10 minus VD over 10,000 I1. That's just the parameters that we have. Okay. So VD is in there. I choose to plug in 0 in here and obtain 0.594 as my answer. 0.594 is my result. My assumption is 0, so it doesn't match. That means my answer is incorrect. So now my next step, I'm going to plug in 0.65. So I plugged in 0.65, and I obtained 0.5923, going up to 4 decimal places. Then I take 0.5923 as my answer, plug it back into the second step, and I obtain answer. Now my answer is 0.5924. It's matching up to 3 decimal places. Okay. But just to show and illustrate this example, I went a couple more times, and you can see here. It's all the way accurate up to 1, 2, 3, 4, 5, 6, 7 decimal places, right? And just finally, I plugged in this value and obtained the same as the input. And so 8 decimal places, it matches up. We just stop there. Okay, iterative analysis. So this is something that we did in that class also. All right, let's go back to R115. And hopefully this makes sense now, right? Let's see. This should be the last slide, I believe. Come on, just in time. I don't know why it keeps doing that. All right, SPICE verification. This is something that you should also do. Again, it's just a SPICE circuit, 10-volt source, 270 ohm resistance, and the 690 diode. Once you plug it in there, you run the simulation, and what do you get? 29.6 milliamps. Okay, 29.6 milliamps. We went only 2 steps in our manual solution, or 3 steps, if you will, and we obtained 30.22 manual calculation. So the error, or our manual calculation, is off from the simulation result by 2%. And that 2% error comes by ignoring the diode resistance of 6 ohms. Okay. 6 ohms is approximately 2.2% of 160, or very close to 2% of 163, which was the original calculated value. Okay. And so we ignore diode series resistance, and then that's what we obtain. Okay. So observations, please read through. Again, solving a linear equation and choosing a starting point. With modern devices, modern spreadsheets, software, tools, programmable calculators, iterating these equations doesn't take any longer than doing one equation. Okay, you press a button and it just solves it automatically. Doesn't take long. All right. Yeah, it might, as it states in the last, result is never actually incorrect, but in the first few iterations, it might not converge or match up. You might have to go 2 or 3 steps, maybe 4 or 5 steps, depending on how many decimal places we want to take. Okay. Yes. In real life, that is a possibility. Oh, I mean, it doesn't match in the first 4. Absolutely, it could happen. But again, it depends on how much accuracy we want. If it's like 29.9 and 30.1, if you're satisfied with that, it's like, and then if it's done with 2 decimal places, then yeah, it's done. Good. Right? Yeah. If you want millivolt, if you want it to match up to the millivolt range, then perhaps 3 decimal places. But beyond that, I don't know. It depends on the specific application. All right. You too. All right. We'll end class here today. Happy Halloween. And I will see you all on Monday. Quiz on Monday based on the material you have covered in this week. All right.